We'll start, Professor. So, hello, everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Gaurav Ghatak. He will be speaking on a new metric for reliability in stochastic geometry. Gaurav Ghatak is an assistant professor at the Department of Electrical Engineering at IIT Delhi, where he works on stochastic modeling of wireless networks. His primary research areas are stochastic geometry and online learning algorithms. In both these directions, he focuses on developing new models for investigating physical and MAC layer wireless communication protocols. Currently, he is investigating the interplay of these two directions to study the spatio-temporal statistics of the performance of learning algorithms deployed in wireless networks. Audience are encouraged to ask questions at any point during the talk. Questions may be asked either by unmuting or speaking directly or by typing them in the chat box from where they will be relayed to the speaker. Over to you, Professor.
Thank you so much for the introduction and for having me again for this CNI seminar series. Um, so, this talk would be about this new metric called statistics of successful transmissions. And it's not really a new metric per se from the perspective of probability, but the interpretation of this from the perspective of wireless communications is something which is kind of new. So the outline for the talk is as follows. I'll start with something called run lengths of heads and tails. So I'll take you all back to our high school days. And for the PhD students in the audience, probably your last encounter would have been during your PhD admission interviews, right? You'll always have some question on uh, uh, coin tossing, right? One particular feature of heads and tails is the run length, and that's what I'll be introducing first. It might not be so straightforward as, let's say, other examples. It turns out that the statistics of run length has been long studied. We'll look at one particular solution which is kind of over 300 years old. It was by other form of de Moivre's solution. And we will see how this solution can be applied to study some features of different types of wireless networks. We'll particularly see two examples. One is restless control systems and how we can use this metric to characterize the controllability of this system. We will also see an example in radar tracking. So how the run length of heads can be used to interpret the tracking probability of targets in an automotive radar system. In particular to this second example, which is the radar tracking, we'll go into a bit more detail on how to characterize it theoretically. And we'll see that from the perspective of some QoS requirements of this radar application, which can vary in terms of the reliability requirements as well as the latency requirements, how those different QoS requirements can be brought back to design a frame for radar tracking. Okay, so without further ado, let's start. So the first thing that we'll be discussing is this statistics of run lengths. And to motivate it, thankfully, we have this example where unfortunately we have, for those of you who follow cricket more closely, you would know that we are losing a lot of sequential tosses, right? In fact, very recently, which was the final of the recently concluded Champions Trophy. With our 12th straight loss, we equaled one of the world records of consecutive tosses lost. Right. And due to the ergodicity of the system, you can say that the probability or the statistics of consecutive losses in case of a toss of a fair coin matches the probability that you would have successive heads or successive tails, for example. It actually occurs more common in real life than we think. So an interesting example is this document called Strong Theorems on Coin Tossing. It's quite old. The interesting thing was, the interesting anecdote in this work was an experiment in which 400 participants were divided into groups of 200 each, and each were tasked with two different objectives. The first group of 200 participants were asked to toss a fair coin. Each of them tosses one fair coin and sequentially note down the output of what comes up, basically sequences of heads and tails. For the other group, the task was to write down what they think would have been an outcome of toss of a fair coin, 200 tosses. It turns out statistically it's possible to detect which is the outcome of the actual toss and which is the outcome of what we believe to be the toss of fair coin. It turns out that the run lengths where subsequent occurrence of heads or subsequent occurrence of tails occurs more naturally even in the toss of a fair coin than we would believe. If we have to simulate it from our idea, we have to write down on the basis of what we believe to be the toss of fair coins. After a few heads, we would believe it's time for tails. So the law of averages is so inherent to us that we would believe that fairness comes up very quickly, but it kind of doesn't so much. We'll talk about this a bit in the beginning. Moving from coin tossing to successes, what does success mean in case of wireless networks, right? Very simply put, let's say we are a user and we have some useful signal and we have some interfering signals. So we have useful signal from a base station with which we have associated to with some association policy, whether it's the nearest one, the strongest one, or most preferred one, or the one where we have access to, maybe it's password protected or whatever. So basically we have some useful signal and we have some interfering signals, right? The individual link powers depend on the distances as well as blocking conditions, propagation of the environment of the propagation, and so on and so forth. It also depends on some random fluctuations, which is your fast fading or your small scale fading, right? The signal to interference and noise ratio has been the key metric in wireless communications. It's the ability to decode the control channel. Basically, if your SINR or signal divided by this interference and noise exceeds a certain threshold, you would roughly call it success in that transmission slot. Remember, there are many random quantities involved here. Even in the signal, there is a random distance to which to the transmitting source or your preferred transmitter. In the interference, there are multiplicity of randomness. There are multiple interfering base stations, the number of which can be random. Their locations can be random. And in addition, each term is weighted by a random fluctuation, which is the small scale fading. Taking all of those into account together, if we are interested in the probability whether my SINR exceeds a certain threshold, people have been calling, or we have been calling it, success probability or coverage probability, or 1 minus this quantity has been termed as the outage probability. Typically, the transmit frequency, given the transmit frequency and propagation conditions, the signal is a function of the transmitted distance and some quantity which is the fading of that transmitting link. While interference is a function of the locations of the interfering nodes, as well as a vector of in most work it is IID fading statistics, but they can be correlated as well. Nevertheless, the model that we have been using is power law for the signal, and the interference is the sum of the power law from the interfering sources. Basically, you sum up a random number of random terms. Right? It's the characterization of these random number of random terms on the basis of their locations is basically the main contribution of stochastic geometry, or the core contribution of stochastic geometry type of works. Now, exact characterization of the randomness of phi and its impact on this probability of success has been the focus so far. Now, people started to realize that phi and xt, which is the location of the interferers and the location of the transmitting antenna or the base station with which I am connected to, are not as agile a random variable as the fading. Right? So, for example, if I am making a call using my wireless device, the location to my serving base station or the location to my interfering base stations or the blockage conditions around me, which is the large scale fading, are not as agile changing random variables as the fast fading. My coherence time is very less, and in between I am not moving so much, so that my entire distance distributions to all these points changes. So they are randomness in different time scales. So the above framework was generalized to meta distributions. So meta distributions was the probability that my SINR, so Xi is my SINR, defined in the previous slide, exceeds a certain threshold given my realization of the locations. So given my realization of the point process and given my realization of the transmitted distance. Now, since it is conditioned on this special stochastic process, it becomes a random variable. It's a random variable which takes on values between 0 and 1. Now I'm interested in the probability that this random variable exceeds a certain value, small t. Now this becomes, oh, so there is a mistake here, so it will be beta, right? So it's a function of two parameters now. Whether my SINR exceeds a certain threshold for a given realization, and whether that random variable takes on a value greater than a certain other threshold. Now, this capital PS is called the conditional success probability. It's the success probability given my network realization, whose mean is the small ps, which is the success probability, standard success probability defined in the previous slide, and its distribution is the meta distribution. Now, why are we interested in this m of beta comma gamma? Because because this meta distribution represents the fraction of links that experience an SINR greater than gamma in beta realizations of the network. So if we calculate the coverage probability or the success probability using my previous formulation, the probability that SINR is greater than gamma, it throws out a number. So it throws out a number such as 0.75, for example. But there can be different types of networks where an example can be all the users are having coverage with probability 0.75. On the other hand, there can be another type of network where some users are really poor, they're not getting the signal at all, while some other users are experiencing very good coverage. Now, this disparity between the experience of these users in the different network realizations are not taken into account in this equation. Whereas if you can have a more fine-grained approach and you separate the degrees of randomness, one due to the locations and other due to the randomness of those locations, you can now talk about how many fraction of links experience an SINR greater than gamma in beta fraction of the network. Okay. Now we are still not satisfied. We would want to even further extend this, and which is the topic of this talk. Now let's assume that given a realization phi of capital Phi, so capital Phi is the spatial stochastic process which determines the location of the transmitting antenna as well as the interferers. Now given a realization of this, and the transmitter attempts to send packets in a sequence of capital T attempts, let's call this a block. So I will make capital T attempts of transmissions. And also, let's say that I will call that block to be successful if my SINR exceeds that threshold gamma in new consecutive slots, that is the event L greater than nu for some nu less than t, where L is the run length. Now, suppose capital T is equal to 10, right? So the scenario is this. I am not only anymore interested in one shot success, but I am transmitting in a sequence of 10 slots, and I will call those block of 10 transmissions to be successful if I have consecutive successes in more than, let's say, new number of slots. So new can be 6, for example. If I have a run length of 6 or more, I will call that block to be successful. Now, the probability of this event is the distribution of the run length, which is the probability that L exceeds nu for a given realization of phi. Now, this again is a random variable because of this conditioning on phi. We can actually extend it even further and talk about meta distribution of the run length, which is the probability that the conditional probability of the run length given the realization of phi exceeds beta. Yes, Professor Mehta, you have a question.
Can you hear me now?
Yes, I can hear you. Yes, please.
Just one question. I just want to understand why is it important that they be successive, the successes? I mean,
Yeah.
if
So
some scenario code, you just care about how many went through, right?
right. So in a few slides later, I will tie this requirement from the perspective of a specific requirement of a control system as well as a specific requirement of a radar system. So the idea, roughly the idea is that, so if you are detecting a target from the radar perspective, if you have a sequence of pulses that you are sending, for accurate tracking, you would want that I am able to detect the target in subsequent slots rather than having missed detections in between. So I will say that my tracking is more reliable if I have a run length of successful detections. Similarly, in control systems, I am sending packets of control inputs from a remote sensing measurements. And let's say if, it's a restless system, so even if I miss one packet, the control system or the actuator evolves to a different state, from which I have to recalculate the control inputs. So from the perspective of restless systems, this framework can be tied to controllability, where you need consecutive successes so as to send consecutive control input successfully. So that's the couple of examples on the top of my mind, actually. Okay, so if that is the case, if I'm talking about the meta distribution of the run length, now this represents the fraction of transmitters that experience a successful transmission in at least new slots in a sequence of T slots for an SINR threshold of gamma in at least beta fraction of the network realization. So now it's a 3-parameter quantity which we are introducing. Gamma represents the threshold above which my SINR should be present. Beta represents the number of or the fraction of network realizations where I would want to give that guarantee. And nu represents this run length which is tied to my QoS requirements, in this example, whether it's radar or control system. So it's a 3-parameter quantity that we would want to characterize. Hopefully this kind of answers the question, I guess. Little bit maybe. Okay, how do we come back to the analogy with coin tosses? So let's consider we have a series of T matches. The physical structure of the coin is random. Let's say phi is the analogy of the randomness of the coin, and hence the bias is random. Now we have chosen one coin phi from the distribution of capital Phi. Now, given phi, there is still randomness, wind speed, force of tossing, who is tossing it, etc., etc. Now we ask, what is the probability that we will win consecutively new tosses or more? So that is the random variable. Now extend it to ask, what is the distribution of the above with respect to the original distribution from which I could have chosen the original coin or the tossing coin. Okay. Given this framework, it turns out the statistics of this quantity has been well studied, as I was mentioning, for over 300 years. So De Moivre had a solution, and the solution is kind of, you can independently derive it as well, and that's what we also kind of did. The combinatorial classes of sequences without a run of m successes, you can write it as follows. The length is less than m to the power k as k goes greater than 0 until t. T is the number of successes. It will be clear from the illustrative figure that I have in the following. Now, every time my SINR does not exceed that threshold, I'll call it a failure. And if it exceeds that threshold, I will call it a success. Now, how do we calculate? So it turns out that this is a summation of CTK nu. Now, this quantity is the number of sequences in T total length, given that you have K successes, how many of them have new or higher consecutive K successes? So you can think about T as is in my previous example, capital T as 10. Now CTK nu represents the number of such sequences in which you have 10 tosses, out of which K successes has occurred. It has been given to you that, let's say, 8 successes has occurred, out of which how many sequences have 6 or more, so nu equal to 6, for example, 6 or more come together. So how many heads, how many sequences are there where there are 6 heads or more together? Now, if I sum up this will be the number of sequences that I have where I have new successes or more. It turns out that there is a very elegant representation for this. Here, my x-axis represents t, y-axis represents k. So we read this table as follows: that out of sequence of 5 tosses, if I have been given that I have 3 successes, exactly 3 successes, and I am interested in nu equal to 3, that means how many sequences occur where those k number of successes have more than nu number of successes occurring together. There, I can just read out the value, and it represents those terms CT K nu. Now, building up this table is more or less straightforward. Initially, it follows something similar to a Pascal's triangle here, but it turns out that there is an elegant formula to it. So basically, in order to fill up one of these cell, you have to start from one of the leftmost cell and go new number of cells diagonally below. So nu equal to 3, we will have nu equal to 1, 2, 3. And if we add these numbers up, we can fill up this cell, and we can actually fill up all of them together. Now, if I am able to fill up this table, then I can talk about the total number of sequences where this occur, and I can also now talk about the probability of those sequences occurring. So for example, if I read out this table for t equal to 5, if I add up these numbers, which is 3, 10, 10, 5, and 1, these are the total number of sequences in which more or less than 3 sequences occur together. And 1 minus of that is more than 3 number of sequences occur together. Now, individually, they are IID. So if k equal to 3, exactly 3, then since individual tosses, given the realization of the coin, or in terms of the wireless communication, given the realization of the spatial point process, individual transmission attempts are independent. The dependency comes from the geometry, but we have conditioned on it. Then, given certain k, I can exactly calculate the probability of these many terms. So each of them have p success to the power 4 multiplied by 1 minus p to the power t minus 4, t minus 3 basically. Now, this can be actually formally put to come back to this summation of this CTK, which has the corresponding counting generating functional. And these are kind of out of a textbook, basically. And if this is my generating functional, my theory says that the coefficient of s to the n in this generating functional gives me the exact probability that my run length is less than m. And 1 minus that would be the probability that my run length exceeds. So we have a denominator, which is a bit weird, but we can expand it using my binomial expansion, and a certain set of manipulation gives this final expression. Now, this expression is present in several probability books. What we would be discussing today is how to use this expression, which is the probability, is the distribution of the run length, in order to gain insights into the communication systems. I think the motivation is, or the context is at least clear, I guess. Okay, so to also answer Professor Mehta's question and to give applications of this framework, think about restless control systems, as I was mentioning, where you have pairs of transmitters and receivers. The transmitters are, let's say, connected to a sensing unit, as well as it is a part of a controller, which sends input signals to the actuator or the control system in a shared wireless channel. And the success is measured in terms of whether the transmitter is able to successfully transmit this wireless channel to the actuator. Since there are many, in this network control system, there are many transmitter and actuator pairs, or the controller actuator pairs. They share a common channel, and we must study some kind of MAC protocol to maximize the probability that the individual transmitters are able to drive the actuators into controllability. Let's take an example. So this is, let's say, how my system evolves. A is my system matrix, B is my input matrix, UT is my input signal. xt is my state. It evolves with the impact of some process noise, and let's say that it is a nice system in sense that it is controllable. If I have been able to drive that system into some desired state, then I will be able to have good enough control inputs or feasible control inputs to keep it in that state. So it's a very strong assumption, but for the moment we can make this simple assumption that the column space of B contains the column space of I minus A, because I want BU to have solutions to I minus A of X desired state. Now this system aims to drive and retain the system at a desired state with a suitable choice of control inputs. Now, the actuator computing capabilities are limited, we assume, so all computations are offloaded to the controller. The sensors observe the state of the system periodically. Let's say observes every capital T number of slots, and T is the block length, so it's a delay between two observations. And the controller estimates the control inputs are needed to drive the system to the desired state and sequentially communicates to the actuator. Now the question is, do these control inputs reliably get through to the actuator? Now think about this successful transmission framework that we just discussed, right? I will call a successful transmission to occur if, first of all, I am transmitting. So C0T represents my transmission state. So whether I am allowed to transmit or not based on some MAC protocol, and whether my SINR is greater than a certain threshold. So my C02T, which is a binary random variable, is the decision of whether I have to transmit or not. In case I transmit, my SINR should exceed that threshold. If both these events occur, I will call ST equal to 1. Now what do I need? The controller, once it transmits, let's say it has a feedback to say whether my transmission was successful or not. Now, for this system A comma B, with nu being the degree of the minimum polynomial of A, the system, we will call it to be block controllable in this block of T transmissions if there is a run length of at least nu ones in this sequence. So I have SKT, in the KT plus 1th block, I have SKT, SKT plus 1, so on and so forth until my block ends. Now in this sequence, if I have a sequence of at least nu ones, I will say that this system is block controllable. It's not a standard definition. We kind of invented this definition for explaining this kind of a restless system. Another example is from the perspective of radar tracking, which I will be delving into more detail. So here a bit of background is necessary. Classically, those of you who have been working on radar systems, the classical parameters of radar systems are detection probability and false alarm probability, which are together called the receiver operating characteristics. So basically, you would want to maximize the detection probability with a constraint on false alarm threshold or something like that, right? Now, why is SINR interesting in designing radar systems? Remember that the false alarm probability is basically whether my total signals, including without the useful signal exceeds the certain threshold. Whereas my signal detection probability is whether my signal plus all the signals that I am getting from clutters and interference that exceeds a certain threshold. So this is an example where I plot the interference and noise, as well as I plot signal plus interference plus noise. Now, if I have a certain threshold, according to this radar system, I will have a false alarm. So it's similar to how we derive the BPS schematic. So I will have a false alarm if my statistics or the random variable interference plus noise exceeds that certain threshold. I will have a missed detection if my blue curve or the probability, the blue curve is below the aforementioned threshold. So the area under the blue curve before the threshold and the area under the red curve after the threshold are of my interest, basically. Now, how is statistics of SINR linked to this? Now, if the SINR is high, I will have these two curves well separated. Higher the SINR, the red and the blue curve will be farther from each other. Now, if they are very far from each other, then I will have more flexibility of choosing that radar threshold so as to have arbitrarily low error probabilities, either in terms of the detection or in terms of the false alarm. So in some sense, the distribution of the SINR, although does not directly tell us the radar metrics of receiver operating characteristics, but it tells us how well a radar system can be designed if my SIN based on that SINR statistics. Now, given this motivation, let's say we would want to characterize automotive radar systems. So I have this ego radar and I am interested in detecting a target. And this is a part of the talk that I kind of presented in my previous CNI seminar series. So I have a structure of streets in an urban area where my interfering vehicles can be present. And the ability for this ego radar to detect the target depends on the signal that you are receiving, also depends on the interference that you are receiving from these other interfering vehicles. It has to be a bit more carefully characterized because not all the vehicles are interfering. So for example, this ego radar A does not experience interference from these potential interferer D, because it does not fall inside the radar beam of that D. Although that vehicle which is present at D is present inside the radar beam of the ego radar. So basically, an ego radar experiences interference from another vehicle if and only if that particular vehicle is inside the radar beam of the ego radar, and simultaneously the ego radar is present in the radar beam of that potential interferer. So we have this double conic section passed through all the interfering point process, which is the location of these interferers, masked with this double conic section, which will be my potential interferers. Since this talk is not about accurate characterization of this point process, I will move through this a bit more carefully. But just to say that we have accurately characterized how much interference realistically an ego radar experiences in real world networks, which is basically related to the street system characterization work, which is a different type of work of ours. Okay, we have actually characterized this interference experience from the perspective of real data. So you think about a scenario. So let's say the right hand maps are of our interest. It's a map of Delhi, the top right corner, but only the Delhi capital region. But we can actually extend our view, and in the extended view, we see that we have more dense sort of streets inside the city center and rare streets outside the city center. So how an ego radar experiences its detection probability will be dependent or contingent on where it is actually attempting that detection. Its experience inside the city center will be completely different than what it experiences outside the city center. We have actually borrowed real data, fitted into our model of line processes in order to characterize the interference process. But again, as I mentioned, we will not go into deeper into this characterization. Rather, let's talk about, so this is an example of how we do the data fitting. Rather, let's talk about how we emulate or how we borrow this, this framework of successful detections into studying this radar network. For that, let's first define a radar MAC protocol. So let's say my time frames are divided into blocks of T slots each as before. Now, in each block, each vehicle operates in that block with a probability delta. Now it's kind of a block aloha. So you compete for access for the block. Once you have access in that block, you have access in that entire block. So within that block, an active vehicle attempts to detect the target in a sequence of T slots. So if you have a larger window, you can have multiple blocks in between, and each block has competition for access, which is based on this block aloha. Once you get access in a block, you are allowed to transmit in all the slots of the block. And each block has T, capital T number of slots. Now, our definition of detection as before is that in case my SINR exceeds this threshold gamma in one of the slots, I will call that target to be successfully detected. On the contrary, if I denote L to be the maximum run length of these successes in a block, we will call L as the tracking length. Again, it's a random variable. We will call a successful tracking event to occur if, or we will define the target to be successfully tracked in a block of length t slots if the ego radar successfully detects the target in new consecutive slots. That is the event that L is greater than or equal to nu for some nu which is less than capital T. Okay. So how do we illustrate it? Or this is another illustration. So you have these kind of total deadline of tracking, which is divided into these blocks. In each block, you are either active or inactive based on your ability to access according to the Aloha protocol. In each block you are active, you are allowed to transmit in all the slots. So transmit in all the slots of the active block. Each slot corresponds to a radar pulse and received echo, and based on that echo, you calculate whether my SINR of this received echo is greater than a certain threshold or not. If it is greater than a certain threshold, I call it success. If it is not, I call it failure. Now, in this sequence of slots inside one block, if I have a sequence of successful detection, I will call it a successful tracking event. So that's basically the overall illustration of the radar map. Now, SINR, as discussed before, is the signal that I am receiving, just a minor deviation from the direct wireless communication of cellular networks. I have the received echo signal, and hence it's a two-way path loss. So it's to the power minus 2 alpha. Basically, I have a reflected signal. So it's raised to the minus 2 alpha. On the other hand, the interfering signals are direct signals from my interfering vehicle. So it's only raised to the minus alpha from the power law path loss. And phi I is a subset of the total locations of the vehicles. And as I mentioned, that it's derived using that double conic structure passed through the entire point process. And that's characterization is not present in that talk, in this talk. So it's basically a subset of the point process of the vehicles which form my interfering set, which mutually cause interference to the ego radar, and the ego radar creates interference to that vehicle. We are interested in conditional detection. So probability that my SINR exceeds that certain threshold given my realization of that locations is given by this equation. It's classical from by the assumptions that we have made based on the fading as well as the location of the point processes. Now, we leverage back the De Moivre solution is that given my conditional detection probability, I can now talk about my conditional tracking probability. That given my locations, so whenever I say given my locations, it has all the baggages of whether I am talking about the city center or the outskirt or somewhere in between. Given my locations means I have already defined where my interfering vehicles are actually present. Given this scenario, now I am attempting transmissions in individual slots, and the experience that I'm having is IID given phi. Now, my conditional tracking probability given phi is, now I exactly use De Moivre solution, where the success probability is now replaced with the conditional detection probability. Now, remember that this is still a random variable because of this conditioning. So what I can do is further study it. For that, we can derive the moments of the conditional detection probability, which is the expected value of the detection probability raised to L. It's the Lth moment. Now, this Lth moment would help us in deriving the statistics of this conditional detection probability, conditional tracking probability. So, the theorem that we have derived is this, that the expected number of successful tracking events across all networks instances where my tracking event is determined whenever I have a successful detection of new slots or more is given by this equation. So it's basically the Lth moment where I sum L from 1 to capital T minus T times the T plus 1th moment. More interestingly, if T equals infinity, which means I can, there is no MAC, I basically have, once I have access, I will continuously transmit forever, which is kind of basically what the current radars in vehicles do. There is no cooperative MAC scheme, right? Then the expected tracking length, that means the expected length of consecutive successes is simply given by the sum of the movements. So that's an interesting byproduct of this result. How do we use all of this result in order to design such a radar system? Before that, let's maybe look at one more example, which is the expected value of the previous random variable. So expected value of the conditional tracking probability. Again, we use the moments to derive this final expression. The derivation is present in one of the references. I'll share this. Okay. To recap, we are interested in successive successful transmissions. From the perspective of radar, it is successive successful detections. We are not only interested in this quantity across all network scenarios, but we are interested in fine-grained approach to this. That means given a network scenario, what is the statistics of this run length of detections? And we are interested in distribution of this run length of detections across different network scenarios. All of this we have characterized theoretically. Now, how do we use it to actually design a system? So let's say I have a latency requirement of my radar, right? So let's say capital TL is the latency requirements. It is specific to a particular use case. It can be different for different use cases. You think about an use case like lane change assistance or a automatic emergency braking, which are very latency constrained. It might have in the order of 1 millisecond or even fewer, because we are talking about the not the end-to-end latency, but only on the radio link. So it can be actually on the order of microseconds as well. On the other hand, there are several radars in your vehicle which have not so much that are not so much latency constraints. You think about parking assist. So your backward-looking radar, when you are doing parking, can have order of several milliseconds in terms of the latency deadline. Now the design is this, that given the latency deadline, you would still have some kind of reliability requirement. That, okay, I have a larger parking assist latency deadline, but I also have a reliability requirement that, okay, I don't want to hit the back wall while I am doing the parking. Similarly, when I am trying to do or I am trying to enforce emergency braking or lane change, I want assistance for lane change. I still want a target detection of greater or target tracking given by this parameter mu. Now, we will call successful event to have occurred or successful tracking event to have occurred, but in that latency deadline, we will say that the use case necessitates that at least one successful tracking event, that is the ego radar, experiences at least one burst of new successes within a deadline of TL. Now, it's a bit important to recap a bit here. So you have a larger latency deadline, which is TL. You can actually break it down into multiple blocks and compete for access in each of these blocks. In any block you have actually gotten access, you will transmit in all the slots of that block. But you will only be saying that the block is successful if you have more than new number of consecutive detections. And I will call that entire use case to be successful in that if inside that latency deadline, I am able to have at least one successful tracking event. Now, how do we design it? So first design choice is that I can divide my latency deadline into n number of blocks, which is not so trivial to decide because there is a trade-off. If I have a larger number of blocks, I will have fewer. If I have a larger number of blocks, then each block would be smaller in size because my latency deadline is fixed. If my each block is smaller in size, although I have larger number of blocks, that means I have more attempts of getting access. Whenever I get access, I will have a very stringent run length in order to have successful tracking. Now, each block is further divided into T slots, which corresponds to one pulse width of the radar. In particular, we have number of blocks as the latency deadline divided by the block length times the pulse width. Now, I will call the probability that the target is successfully tracked in at least one of the tracking attempts within the latency deadline, which is given by this equation. So again, there is a typo here. So PT should be inside with delta. So delta times PT is the event that I get an access as well as I am able to successfully track. the probability that I will be able to achieve this in at least one of the blocks is 1 minus, or I will achieve this in none of the blocks is 1 minus Pt raised to the n, delta Pt raised to the n. And 1 minus of that is that I have at least one event where I have successfully satisfied the QoS requirement of that use case. Natural trade-offs arise, as I mentioned. Fewer blocks, lower access chance. However, it results in larger T blocks. So if I have fewer number of blocks, then fewer number of vehicles get access. But those vehicles who do get access, they will have larger block sizes to have successful tracking ability. So the optimal frame design is thus. I want to maximize my tracking probability, the PT inside this parenthesis, such that my number of blocks is limited by the pulse width as well as the latency deadline. And I want to find out that Aloha parameter which maximizes this. Now, there are some observations. The parameters lambda, lambda L actually may not be known by the ego radar. I mean, we are still not in the framework of connected vehicles, right? So there is a chat. No. We are not in the framework of fully connected vehicles. So there is no network which is broadcasting optimal Aloha parameter to all the vehicles which are connected to it. In practice, the vehicle should have to learn these parameters on the basis of successful or unsuccessful detections whenever it is deciding to transmit. Nevertheless, this necessitates the development of data-driven algorithms for optimizing this tracking performance. Nevertheless, we can have some critical remarks, which is, let's say I have delta equal to 1, which is no MAC protocol. Everybody accesses or everybody tries to access all the time. In this case, regardless of the value of nu, we see that the optimal solution is n equal to 1, which means if everybody is accessing, there is no meaning in creating blocks within that latency deadline. You should have one block with the entire latency deadline as the budget. Because since everybody is accessing anyway, you would want to give them a larger block length in order to achieve the possibility that there is a bunch of successes occurring together. The case when nu equal to 1, you can bring back the detection probability, which means you are not interested in tracking. You are satisfied as long as you are able to detect the target only once, which is okay for a static target, for example. The optimal delta decreases with an increasing lambda, which is obvious because interference increases. So for a given block size, given block length, and given tracking requirement, the optimal delta can be read out from an appropriate lookup table. Optimizing the number of blocks is a bit non-trivial because each time you increase the number of blocks, you divide or you decrease the block length geometrically. So if you had the entire latency deadline with one block, if you decided to have 2 blocks, then the block length reduced by t by 2, reduced to t by 2, right? So then you have a more detrimental effect on the tracking probability by increasing the number of blocks. So this increasing number of attempts is counterbalanced by this decreasing blocks. So it has a more detrimental impact. We'll see some numerical results. So I have a few parameters taken from this 3GPP service requirements of enhanced V2X scenarios, which is basically the latency requirements. The reliability, it's kind of heuristic. We do not have any reference for taking these values, but it's kind of an indicator of the relative importance of reliability for these different use cases. So a blind spot detection might need a lower value, or a park assist might need you only to detect it once every latency deadline. You might only want to detect the wall once within the deadline in order to find out where it is. And the next detection can happen in the next latency deadline. Whereas for automatic emergency braking, pedestrian detection, lane change assistance, you might want a higher reliability requirement. The latency requirement can be very low for intersection management, AEB, these kind of frameworks, while it can be very high for applications such as park assist or DSP. For each case, we have solved this previous optimization problem numerically in order to find out the delta star. We'll look at a couple of quick results to see how this behaves. The first important takeaway that I would like to express from the numerical results is this. The optimal Aloha parameter that maximizes the detection probability is not the optimal Aloha parameter, which maximizes the tracking probability. You think about it from the perspective of control systems. The optimal, I'll give an analogy. The optimal Aloha parameter, which maximizes the transmission success, is not the optimal parameter which maximizes the controllability, block controllability of the control system. So this already tells us that there is inherent need for co-designed systems. So if the control system is taken as a black box and you optimize the communication system, you will be coming up with Aloha parameters which maximizes the communication success. But since we have this block type access protocol, and in each block, if you once have access, you will have the ability to transmit in all the slots of that block. So you can afford to sometimes not have an aggressive Aloha parameter, because all you need is one access in one of the blocks. Because once you have that access, you would want the other transmitters to not transmit so as to reduce the interference in order to maximize your controllability requirements, and in this case, the tracking requirements. So that, in my opinion, is one important takeaway, that whether it's a radar system or a control system, the communication and tracking framework and the communication and control framework needs to be co-designed based on the requirements of that system. So motivation to do co-design systems. Another example is finding out the Aloha parameters from the perspective of the tracking probability. So if you have, so let's start with this green curve where we have a stringent latency deadline, 3 milliseconds, and a very high reliability deadline. So you would want to have more aggressive Aloha parameters. It's not, again, trivial to find out, not trivial to claim whether a larger Aloha parameter is better or lower. It depends on case to case. More aggressive Aloha parameter gives you more ability to, or gives you more blocks of access, but also it increases the interference. So there exists optimal Aloha parameters for different use cases. Another example is this lane change assist. We have a very large latency deadline and a lower value of reliability as compared to automatic emergency braking. But since we have a large latency deadline, we can actually not be very aggressive with the Aloha parameter. We can keep it very low, because all we want, because of this large latency deadline, we have several blocks. So all we want is access in one block. And whenever I have access in one block, I want very less number of interfering elements for me. So I can have a lower value of Aloha parameter in that case. So case by case basis, we can actually interpret what would be optimal transmit strategy or MAC protocol for these cases. The final part that I would want to discuss is the non-triviality of the block design. So you think about, for a given latency requirement, I can have one block, which is this blue curve. If I have one block, I have a certain Aloha parameter which is optimal for it. But I can also have two blocks, thereby reducing the size of each block. But I have now two attempts to gain access. So I can actually improve upon my tracking probability. But we notice that the optimal Aloha parameter has now reduced, which is intuitive because I have now two attempts of access. So even if I have a lower probability of access, I just want one access in, it's enough for me to get access in one of the blocks. The interesting part is that the optimality of this red curve is higher than the optimality of the blue curve, because sometimes the cost that we pay by reducing the size of the blocks is overcome by the increasing in the number of blocks, as I was mentioning the trade-off. But in our results, there are very few cases when this happens. The cost that you pay by reducing the size is more detrimental than having more blocks of access, which also tells us that although there has been a lot of work going around in developing autonomous systems and how they interact with each other, autonomous driving systems, and do we actually need to design a distributed MAC protocol for them to interoperate? Okay, given that there will be very dense vehicles and too much interference scenarios, and if everybody accesses, probably no one gets. But if you have an inbuilt MAC protocol or you're studying a MAC protocol, in our opinion, based on these results, it might not be that big a deal. And ideally, the protocol should be everybody, I mean, what is currently being done. Everybody should be trying to access all the time anyway. But it needs further investigation as well. Okay, so what are the key takeaways? We proposed a new metric in stochastic geometry. So the success probability, conditional success probability, meta distribution of success was already existing. We just extended this framework to talk about successive successful detection and employed it to characterize the tracking probability in automotive radars. And in another example, the block controllability in restless control systems. I assume that there might be more examples where you would want successive successes. But in many cases, you might not want them to occur successively, and in which case the analysis is more trivial. Based on this framework, in a block Aloha channel access scheme, the Aloha parameter that optimizes the detection probability may not be the one that optimizes the tracking probability. The analogy is that the one which optimizes the successful transmission probability may not be the one which optimizes the controllability of the system, hence need for co-designed systems. Now, the tracking event can be designed based on the latency and the QoS requirement of the application. So if you have a latency deadline and a reliability guarantee requirement, you can have an optimal frame design to find out what would be the optimal access parameter. But in our results, we conclude that in most cases, unless the scenario is too dense, having a MAC protocol imposed on top of this radar functionality is detrimental due to reduced block sizes. So that brings me to the end of the talk. I'll probably take more questions if there are any.
Thank you, Professor Gaurav, for an informative talk. I request the audience to ask questions if any.
It seems that there
Yeah.
are not.
I hope
But in
everyone.
case if you have, please feel free to write to me.
Yes,
I would be happy to.
I think everyone got utmost clarity from your talk, Professor. So, yeah, thank you very much for accepting our invitation and giving a talk. And thank you everyone for attending and have a great evening.
Thank you. Thank you for having me again.